All right, so now that we've talked about the basics of an exponential growth and an exponential decay function, let's talk about some transformations. Now, the thing about these transformations, if you remember how we transformed those sine and cosine curves, the numbers kind of in the same position do the same kinds of things. If you remember how we transformed rational functions like up, down, left, right, numbers in the same kinds of positions do the same kinds of things. So if you look down here, you've got different variables. You've still got the parent function, okay, with your base of b, the a being out front and the x being the power. But now what do those different things do? So the number that's with the x in the exponent, like you would have to put it in parentheses for the exponent piece, okay, that number does the same thing that any number would do in parentheses with an x. That number up top with the x is the horizontal shift. And this is the one that's backward from what you think it should be. If it's plus a number, it actually goes left. And if it's minus a number, it goes right. Okay. The k out back, or whatever number is out back, does that same vertical shifting. Okay. It's the up and the down piece. So k is the vertical shift, okay, that number out back, and it behaves as we think it should. If you got positive or plus something, the graph moves up. If you've got a minus something, the graph goes down. The number out front here, okay, does the same thing that a number multiplying a sine or cosine curve would do. That number out front is going to create some vertical stretching and shrinking. But first of all, if that number is negative, then the graph is reflected across the x-axis. It turns it upside down. Okay. Then, if the absolute value of that number is greater than 1, so if it's a 2, a 3, a 4.5, a 7.5, that's going to represent a vertical stretch. It'll get steeper much more quickly, but it will also flatten out much more quickly. If that number, if the absolute value of that number is between 0 and 1, so if it's a fraction, that's going to be a vertical shrink. Okay, so it won't flatten out, or it won't increase quite as steeply. So what the first set of problems wants you to do is basically, without turning on your calculator or anything, can you identify the parent function and then tell what transformations are happening? Okay, so, and again, on your homework, you'll have to do this as well. The parent function is whatever the power and the base together are. So like on number 1, the parent function would be 3 to the x power. That's like your basic function. That's something we would have graphed a few minutes ago. Okay, and then to describe the transformations, well, what does that plus 5 do that's just been added on to the end? Good, up 5. Okay. And the more you add on, it does get a little bit tougher to pick out the parent function, but just locate your power of x, locate your base, and that's going to be your parent function. So for number 2, x is my power right there. What is my base? A fourth. So my parent function is 1/4 to the x power. That will be a decay function. And you kind of need to think about that before you actually look at a graph on your calculator to make sure you kind of know what you're looking at. Now, each additional number does something different. Like this 2 out front. How does it affect the graph? Now this number here would move it left or right. Okay, the number that is up there with the x in this original is called h. We'll move it left or right. Okay, so the 2 causes a vertical stretch. Good. And I usually put by how much. It's a vertical stretch by 2. Now, vertical stretches and vertical shrinks are kind of tough to see on an exponential function, so that's why you need to know what these numbers do before you ever look at your calculator. And then that -1 moves the graph right 1. Okay, because any number up there with the x moves it right or left, and it's backward from what you think it should be. Okay, so then on number 3, if you locate the x, which is your power, and then your base, the parent function is 4/3 to the x power. Again, that would be a growth function because that fraction is bigger than 1. Okay. It is flipped, right? That negative out front flips it. So I'm going to say that's an x-axis reflection. If you tell me it's flipped, that's fine too. Okay. What does the plus 2 do that is with the x? Good, left 2. And the plus 7 that's out back, what does that do? Good. Okay. And then lastly, number 4, the parent function, y equals what? 5 to the x power. Good, because my base is 5 when my power is x. All right, what does the 1/2 in front do? Good, it's vertical, and is it a shrink or stretch? It's actually a shrink, okay? Vertical shrink by a half. Okay. And then what does the 4 that's sitting up there with the x do? Good, right, 4, and then the 2 out back moves it down 2. Okay. So before we start looking at graphs, you do need to be able to look at your functions and anticipate what each of those numbers is going to do to the shape of your graph. All right, so as we look at the next few examples, I already have the graphs sketched in, and really I just did that by picking some nice points from my table. Please practice keying those into your calculator, because like on number 5, you do need to have parentheses around the x plus 5. So just make sure you have your parentheses in the right places so that you can make sure you're getting the correct graphs. But also knowing what those transformations do can help us sketch those graphs more quickly than even putting them in a calculator and getting a table of values could. So when you look at number 5, 2 to the x will be my parent function. So what would the plus 5 do to the graph? Right. Or correct, I guess I should say. And now the domain. Still, you can plug in whatever you want to. Domain is still all real numbers. Goes left forever, right forever. Okay. This time, though, some of the other pieces have changed. For instance, the y-intercept is no longer visible on this portion of the graph. You can find it 2 ways, though. You can plug in 0 for x right here. That'd be 0 plus 5, so that'd be 2 to the 5th power, so that'd be 0.32. Or you can find it in your table. There's no vertical shifting, okay? So the horizontal asymptote is still at y equals 0. Okay, so the left-hand end of the graph is leveling out at 0. The right-hand end of the graph, even though it's slid over to the left, this is still the right-hand side of the graph. It's going forever up and forever to the right, this piece here. So it's still going up forever. So my range, just like some of the other ones, is still going to be leveling out at 0, but going up forever to positive infinity. Okay, so that shifting left didn't really adjust anything except the y-intercept. All right, so when you look at the next one, if 1/3 to the x is the parent function, what does the negative or the -2 do to the graph? Good. Now, this is the first time we've seen a vertical shift. So everything is going to be shifted downward, including where the graph levels out. This graph is not leveling out at 0 anymore. Where is this graph leveling out? -2. Okay, so that vertical shift, if you can pick it out, that vertical shift will give you a healthy clue as to where your horizontal asymptote is. Okay, so that whole graph is shifted down to including the asymptote. Okay, but after that, I mean, the points are on there just from the table. The domain, still the same. Okay, range. Now that does change because your horizontal asymptote has changed. Okay, the left-hand side of the graph here goes up forever. But where does the right-hand side of the graph go? Right, -2. It's leveling out. This right-hand side of the graph here is leveling out at -2. Okay, horizontally it's going to the right forever, but vertically it's getting closer and closer and closer to that -2. Okay. The y-intercept, well, previously on all those original growth and decay functions, the y-intercept was always at 0, 1. Well, since it got moved down 2, the y-intercept is now at 0, -1. And you can get that from your table. You can get that by plugging in a 0 for x right there. And then the range. If you can tell about end behavior, that clues you in as to what the range will be. Good, -2 to infinity. Okay, because one end, the left-hand side, is going up forever. The right-hand side is leveling out at 2, so we put a parenthesis, I'm sorry, -2. So we put a parenthesis because it never actually gets there. Okay. So same kinds of things. I'm just going to talk through some of this stuff to make sure we get through. So on number 7, this 1/2 causes a vertical shrink. This +1 causes a vertical shift of up 1. So that means that graph, since the whole thing has been shifted upward, the horizontal asymptote is now at +1. Okay, domain is still all real numbers. Range then starts at 1 and goes up forever. Right-hand side goes up forever. Left-hand side levels out at 1 over here. And again, the y-intercept you can get by plugging in 0 for x, or you can get from your table. The y-intercept, I believe, is the point 0, 1.5. And now you're starting to see some decimals in there, and that's due to that to that vertical shrink. Okay, when you multiply a number by half, you're going to introduce some decimals, some more fractions in there. Okay. Number 8. Okay, again, because your base is bigger than 1, that's going to be an exponential growth curve. This -4 shifts the graph to the right 4 units, and this -5 shifts the graph down 5 units. So since the entire graph has been shifted down 5, 1, 2, 3, 4, 5, your horizontal asymptote will be at y equals -5. Okay. The domain is still all real numbers. The range, you're going from -5 to infinity. Right hand goes up forever. Left hand side levels out at -5. And the y-intercept this time, you will wind up rounding if you look at your table. Okay. But your y-intercept is something like 0, -4.80 something, maybe 0.2. So we're around that. Okay. So when you are, just kind of generalize before we do that last graph, your domain for these exponentials, always all real numbers. The graph does not break apart. There are no holes. You can plug in whatever you want to. Okay. The range comes from picking out where your horizontal asymptote is. Okay. One end is going to go forever. The other end is going to level out at that horizontal asymptote. Okay. The last graph is the only one that is turned upside down. And what is it that made that graph turn upside down? Good. The negative out in front of everything, that negative in front of that 2 is what turned that graph upside down. So that's what gave us our x-axis reflection. Now, while we're here, the 2 creates a vertical stretch. Doesn't matter that it's negative. The negative flips it. The 2 stretches it vertically. Okay? Then the only difference, the y-intercept, the asymptote is at 0 because there was no vertical shifting. But this graph does not go up forever. The right side goes down forever. The left side levels out at 0. So the range is switched around a little bit. and that it goes down forever, so negative infinity to 0. But the domain